Dear students, now in this class we discuss introduction to polymers, the terms involved in the polymers, and also types, thermoplastics, thermosetics. Now come to the polymers. Polymers is a Greek word. It is derived from the two Greek words, combination of two Greek words, poly and mer. In Greek, poly means many, mer means part. So here we combine together, we call as a polymers. So we can define this polymer as a macromolecule built up by linking together of small molecules. These small molecules are called monomers. And here you can see this polyethylene and here polyvinyl chloride and polypropylene. Here these are the small molecules, they combined, and here this is one more ethylene monomer, this is one ethylene monomer. These monomers are the small molecules, they combine together to yield a big molecule or macromolecule which is called as a polymer. Now here this is polyethylene formed by the combination of small molecules monomeric units ethylenes. So here in this polymer the repeating structure, the repeating unit of this monomer is called as a mer. You can see here this is ethylene mer, and in this polyvinyl chloride we can see vinyl chloride mer, and also in polypropylene we can see 2-methyl methyl ethane. So these are the repeating units which are called as mer. Now one more time we define the polymer. Polymer is a macromolecule built up by linking together of small molecules called monomers. The repeating unit in the monomer is called as mer. Now the chemical reaction which yields a polymer is called polymerization reaction. The process of chemical combination of small molecules to form larger sized molecules is called polymerization. Here we can see example, the polymerization of ethylene. This is a ethylene monomer. N number of monomers are taken here, and polymerization reaction, they are linked together to form a large molecules. So here these ethylene molecules taken n times. It indicates that n times ethylene molecules are repeated in this polymer chain. Similarly, polystyrene, we can see here this is the styrene or vinyl benzene on polymerization formed a polystyrene long chain, polymer chain. Now, and one more term, that is degree of polymerization. Degree of polymerization is nothing but the number of repeating units in the polymer chain. The number of repeating units in the polymer chain is called degree of polymerization. Here this degree of polymerization varies from 500 to almost 3 lakhs. Here you can see we are mentioning this unit. It is a polyethylene polymer. So here it is repeating n times. This n is nothing but a degree of polymerization, the number of repeating units in the polymer. When these polymers, the degree of polymerization vary with is more, okay, very high. Such polymers are called as high polymers, and low degree of polymerization polymers are called as oligomers. Next, the important one, functionality. Actually, because of the functionality only we are able to form the polymers. The functionality is nothing but the number of reactive sites or bonding sites present on a monomer. The number of reactive sites or bonding sites present on a monomer responsible for the polymerization. Here you can see this is a ethylene molecule, and we have a double bond. This double bond upon instigation, so we can break this bond either by heat or light or any catalyst we can use to break this bond, so that here we may get two active radicals. Two active radicals are sites, bonding sites. These bonding sites can link with the adjacent another bonding site, so that a chain elongation takes place. In this way a polymer is formed. To a monomer must be at least bifunctional to form a polymer. Only at least bifunctional. A monomer must have at least two reactive sites on it, so that it can form the polymer chain. And monomers with one active sites never form any polymer. So it is essential that each and every monomer at least bifunctional in nature. So here a few examples. Ethylene here you can see this double bond. So breaking this double bond we can get two, this is one and this is one, two active sites on it. Similarly vinyl chloride, this is one carbon and this is carbon, two active sites by breaking this double bond. Similarly 1,3-butadiene, here you can see two double bonds are present. So two or sometimes many double bonds may be present, but during polymerization reaction these bonds will break and rearrange to make it to become a bifunctional monomer. See here, on heating or by instigating by heating or light or using any catalyst, we are able to break double bonds, and this here one radical formed and here one radical formed when you break this double bond. Similarly here one carbon radical formed and here one carbon radical formed when we break this double bond. Now this radical and this radical combine to form a double bond over here. You can see this. Okay, here now here one active radical and here we have one active radical. In this way a poly bonded when a monomer contains more number of double bonds, two or more number of double bonds, it will rearrange to make it as a bifunctional monomer. So you can see this type of arrangement in 1,3-butadiene, even in the isoprene. Now these are a few examples. Not only double bonds, some monomers may have polar functional groups. Here this is a carboxylic acid functional group, and here also another carboxylic acid functional group. So end to end this carboxylic acid can it may lose its hydroxyl group, or this side hydroxyl group or acidic hydrogen group by linking with the another acidic group or alcohol or amine, any other monomer which is having a polar functional group affinity towards each other. Similarly here two amino groups, this is one amino group, this is one amine group. Two amine groups are present here. This amine is capable to lose the hydrogens. So any polar monomer having polar functional group, suppose if we take a carboxylic acid functional group on this side, so OH C double bond O, in this way we have a polar functional group, so it is ready to lose its water molecule in this way, and a bond is formed between the nitrogen and carbon. Now this 1,6-hexadiamine is a bifunctional monomer. It is a polar functional group. Similarly terephthalic acid, see on terephthalic acid we can see two carboxylic acid groups. Similarly ethylene glycol, two hydroxyl groups are present. These two polar functional groups are capable to link with any other polar functional group which have affinity towards each other. And terephthalic acid, ethylene glycol, 1,6-hexadiamine, all these are the bifunctional monomers. Next nomenclature. So nomenclature, first we discuss homopolymer. Homopolymer, it consists of identical monomer units. Identical monomers units. The polymer chain, when you check here, one example, polyvinyl chloride. See, this is one vinyl chloride unit, and this is another vinyl chloride unit, and this is another vinyl chloride unit. In this way, all the monomers are identical in nature. Such a polymer is called as homopolymer. Here we have many examples like polyethylene, polyvinyl chloride, Teflon, etc. Next, copolymer. So copolymers, they are formed by two or more monomers of different chemical structure. Two or more monomers of different chemical structures combined to form the polymer. They are called copolymers. Here, styrene butadiene rubber we take as example. Here, this is a styrene monomer unit, and another monomer is butadiene, 1,3-butadiene monomer unit. In this polymer chain, we have two different monomers having different chemical structure. Such polymers are called copolymers. Next, based on their structure also, we can classify them into linear polymers, branched polymers, cross-linked polymers. Linear, you can see all the monomer units are combined linearly. Here they are in the blue color, so this is one monomer, this is one monomer. In this way they are combined with in a linear fashion. Next, branched chain. The monomer chain, the long chain or the backbone of the polymer chain will contain small branches to it, attached to it. Such polymers are called as the branched chain polymers. Here this is one branch, and here this is one branch attached to the backbone of the polymer chain. And cross-linked. Cross-linked means adjacent polymer chains may have a linkage with the other chain. So this is one polymer chain, this is one polymer chain, and they are linked with the another cross-linking. Such polymers are called as the cross-linked polymers. And one more special type of polymer, that is graft polymer. It is a little different. Here the monomers of the main chain or polymer backbone chain, and the branches of the monomers attached to it, they are different. Okay, so here this is the A molecules are the monomers of the carbon or the polymer main chain, and these B molecules are different from that main chain, and such a polymer is called as graft polymer. Next, this is very important, the heat. Based on the response to heat, the polymers are classified into two types: thermoplastic polymers and thermosetic polymers. Thermoplastic and thermosetics. Come to the thermoplastic. Thermoplastics are softened on heating. Since they are softened on heating, we can remold it, we can reshape it, or we can return from the waste and we can reclaim it. And these thermoplastic always soften on heating and hardened on cooling. The reason for the softening of these thermoplastics is the adjacent polymer chains. See, this is one polymer chain, okay, and this is another polymer chain. So here this is another polymer chain. In these adjacent polymer chains held together with weak bonds. Here you can see they are indicated in the red color. They are the weak bonds. These weak bonds may be hydrogen bonds, van der Waals forces of attraction, or dipole bonds. Hydrogen bonds, van der Waals force of attraction, dipole bonds, they are very weak. When upon heating, these bonds, they lose their strength, they disappear on heating. That is the reason there is no linkage between two adjacent polymer chains. They slip on each other, they are free to move, so they slip on each other so that they are softened on heating. Again, on cooling, those bonds will appear again so that it is become harden. Now come to the thermosettings. Thermosetics, they retain their structure on heating. They retain their structure on heating. They are never softened. Upon overheating, so themselves they form a infusible mass. Overheating leads to catching fire. Here, the reason for this thermosetting polymers, they are not hard, cool, softened on heating because the adjacent polymer chains are held together with covalent bonds. These covalent bonds are retained on heating. Now, if we compare or when we check the differences between the thermoplastics and thermosetics, thermoplastics are softened on heating, hardened on cooling, whereas this is a thermosetics. These thermosetics here, they are never softened on heating. On prolonged heating, they may catch fire. And also, thermoplastics are generally formed by addition polymerization reaction, whereas thermosetics are formed by the condensation polymerization reaction. And mostly thermoplastics are long chain linear molecules, whereas thermosetics may have three-dimensional cross-linked network structure. And in this thermoplastics, adjacent polymer chains held together by weak van der Waals forces of attraction or dipole-dipole bonds or hydrogen bonds. And in thermosetics, they are held together with strong covalent bonds. These covalent bonds cannot be broken by heating. And since the thermoplastics are softened on heating, we can remold it, we can reshape it, and also we can reuse and we can reclaim from the waste. We can recycle the thermoplastics, which is not possible in case of the thermosetics because they are not softened on heating. Thermoplasts, almost all the thermoplastics are soluble in organic solvents, whereas these also thermosettings are insoluble mostly. And when we see their physical characteristics, thermoplastics are soft, weak and less brittle. Thermosets are hard, strong and more brittle. And these are the examples. Polyethylene, polyvinyl chloride and Teflon are the best examples for thermoplastics. And bakelite, urea formaldehyde resins are the best examples for the thermosettings.